Hello, everyone. I'm delighted to share our latest research findings published in iMeta. We found that the long-term intake of milk fat does not significantly increase the blood lipid burden in normal and high-fat diet-fed mice. Milk, a natural food consumed by humans for over 1,000 years, is one of the world's most important food sources. The impact of dietary fats on cardiovascular health remains debated. Studies on milk fat's effect on blood lipids are mostly retrospective and often affected by inaccurate dietary and confounding factors. Milk fat contains beneficial components, but how their combined effects influence blood lipid health is unclear. Gut microbiota and their metabolites, which affect the host's metabolism, are also important. Whether long-term consumption of full-fat milk is suitable for different populations is a key unresolved issue. To address these questions, we conducted a study using genetically uniform male C57BL/6J mice, subjected to normal diet, ND, or high-fat diet, HFD. Mice were fed milk fat or whole milk for 7 weeks, roughly equivalent to 5 to 6 years in humans. We closely monitored blood lipid levels, dietary intake, gut microbiota, and metabolites. Data were analyzed using machine learning algorithms, with a training set, 90%, and test set, 10%, to explore the impact of different interventions on gut health and lipid metabolism. After 7 weeks, milk fat and whole milk did not significantly increase body weight compared to controls. Furthermore, low-density lipoprotein cholesterol, LDL-C, levels remained stable in both ND and HFD mice. Interestingly, high-density lipoprotein cholesterol, HDL-C, known as good cholesterol, was significantly elevated by milk fat and whole milk, even though HDL-C levels were already high in these mice. As expected, HFD reduced gut microbiota diversity. While milk fat and whole milk increased the Amplicon Sequence Variants, ASVs, in ND mice, they could not fully reverse the reduction in microbiota diversity caused by the HFD. This suggests that the impact of a high-fat diet on gut microbiota is more significant than that of milk fat or whole milk. However, several bacterial species induced by milk fat and whole milk were significantly correlated with LDL-C and HDL-C levels, with 11 unique bacteria showing bidirectional regulation of these lipids. Given the critical role of metabolites in lipid metabolism, we analyzed fecal metabolite profiles in both ND and HFD mice. Long-term milk fat intake in ND mice led to the downregulation of 3 metabolites and the upregulation of 5. Whole milk downregulated 13 metabolites and upregulated 9. In HFD mice, milk fat downregulated 75 metabolites and upregulated 49, while whole milk downregulated 3 and upregulated 4. Notably, several metabolites were correlated with LDL-C and HDL-C levels, with 6 unique metabolites induced by milk fat showing bidirectional regulation. To better understand the complex interplay between gut microbiota, metabolites, and lipid metabolism, we applied machine learning models. These models incorporated mouse weight, food intake, diet, microbiota, and metabolites as input features. The SHAP algorithm identified 20 key features that significantly contribute to predicting blood lipid levels, with metabolites being the most influential. Using these key features, we developed a predictive machine learning model for blood lipid levels. The model demonstrated high accuracy, with our superscript 2 values of 0.96 for LDL-C and 0.89 for HDL-C, when using fecal metabolites and core microbiota as input. The model highlighted a complex regulatory network among metabolites involved in lipid regulation. Our study demonstrates that long-term milk fat intake does not significantly affect body weight or blood lipid levels in ND or HFD mice. The machine learning model based on differential gut microbiota and metabolites accurately predicted blood lipid levels. These findings enhance our understanding of the long-term effects of milk fat on lipid health and provide data support for global nutrition policy development.